Okay, we're now reviewing Unit 8. This is all on, well, let's see, first let's write Unit 8. So Unit 8 review here, and I'm going to try and keep this shorter than I've done the other ones for a couple reasons. One, time's going to be a factor for me, and two, this whole unit is really based on two simple principles, and it's all about variations of new polygons, mostly regular polygons, but we do more than that. Understanding the term regular is going to be important here, and circles. Now, we only did one day on circles, but it's still kind of a big concept because it ties into everything that regular polygons are not, because it's that concept of infinity, knowing that there's like infinite number of sides, or in this case, really no sides. A circle is just it applies that same notion. So since everything's tied into this, and we really built up through this by learning about triangles and how the quadrilateral is an extension of that, and how other polygons are extensions of that as well. So trying to dive into that, we'll see if we can keep this good and short, especially because I'm not really going to do full examples if I can help myself. And I just want to be able to tie in the concepts that you can understand and know, and any examples that you've done before should suffice for you. Especially since we're hitting a bunch of new standards. We're always going to hit standard 1.0 or so it seems. And we're jumping back into standard 7.0, but before we did the portion that involved parallel lines and angle relationships. And I hope that you actually read the full standards someday, and you'll see that 7.0 is a really long standard. So I'm just hitting this part, and this should actually say circles and quadrilaterals. It should say circles, I think, and their properties. And I think it says it on your sheet. Probably going to erase that if it runs into me. I'm actually going to jump around these numbers here and find the best order that I think fits this most appropriately. So I won't go straight up in order because I'm going to do circles last. 7.0 last. Let's start with 1.0. Properly applied terms, theorems, axioms, and deductive reasoning. And there's not going to be so much in terms of theorems this time around. In fact, I can't really think of many theorems that we've even talked about. Most of it's going to be the new terms you've learned, how they come into play, etc. So let's start listing some terms. Let's start thinking about how we came to be here. We began with a polygon, I'd say. Okay, and a polygon is a shape. It's something that's hopefully enclosed, and it has sides and it has angles, etc. Quadrilateral is a polygon, much like a pentagon, etc. They keep going. They don't have to be congruent, anything like that, but I believe they have to be enclosed. And here's something else we didn't really talk about, but here's another quadrilateral. 1, 2, 3, 4. There we go. Here's another quadrilateral. It's 4 sides. Just because it goes inward doesn't mean it's not. Now, the difference between these is this one's called convex. This one's called concave. Ideally, that should make sense that these are both 4-sided shapes. It's just we never see them this way. Making sure that you get that. And then we have regular polygons, which are polygons that have all sides congruent. So I'll actually just use the shape tool here. Let's go to one. Let's go to this hexagon right here. Grow one. This is a regular hexagon. By all intents and purposes, assume it's drawn to scale here. You got sides congruent, all the same length. Angles congruent, all the same measure. And going off that, let's keep talking about. Let's use this hexagon and start marking some things up. These are called the interior angles. They're the angles which we commonly refer to whenever we talk about angles. They're the ones inside the polygon. And they essentially make up the polygon. Same with these guys. These would be interior angles. Doesn't matter that that one's bigger there. It's still an interior angle. So you can tell it looks like they can be greater than 180 here. But in a regular polygon, they're less than 180 and they're greater than 0. Let's see. We've talked about exterior angles adding up to 360. You know interior angles don't always add up to 360. That's only true in quadrilaterals. You know, in triangles, for sure that they don't, because we talked about it all semester. We say that interior angles add up to 180 in triangles. It doesn't matter if it's equilateral, etc. They add up to 180. So you know they don't always add up to 360. So try and keep that idea out of your mind. The ones that do add up to 360 degrees every single time are exterior angles. So we'll be sure to note the difference right now as we talk about it. So interior angles are the ones on the inside. Exterior angles, if I draw and extend my sides here, then I create these angles which are supplementary to my interior angles. And these are the ones they call exterior angles. They're supplementary to them, and they happen to be the same measure as your central angles, which I'll draw in a second. But these are supplementary, so they add up to 180. So if I know the measure of one of them, I can honestly and easily get the measure of the other. If I know one exterior angle is like 40 degrees, I know this is 140. Now, exterior angles always add up to 360. Okay, so this plus this plus this plus this plus this, etc., they all add up to 360. And what's special about exterior angles here is we can use that concept and say, okay, what if we have a regular polygon where all angles are congruent? And by that I mean interior angles. If all interior angles are congruent, then all exterior angles are congruent, which means if I want to find the measure of one exterior angle in a regular polygon, the only information I need to know is how many sides are in that polygon. So if I know this is a 6-sided polygon, a regular hexagon, then I know all of these exterior angle measures are 360 divided by 6, 60 degrees. They all must be 60 degrees. They all add up to 360. There are 6 of them, and they're all congruent. So 60 times 6 is 360. So if I know that angle measure now for all exterior angles, then I know the interior angles are 120, because that's subtracting from 180, etc. So there's like a progression system that you can work here just based on one bit of information, and that's really all you need to know. Maybe you don't even know the number of sides. Maybe they give you what the shape is. And I think that's probably a good thing to jump to next here, just making sure we know our shape names. I'll just go through them right here and just look at them. You're going to have to write them down if you'd like. Triangle. Make sure you're looking up here. Look up here. Triangle. Quadrilateral. I'm sorry. Let's go with the, okay, yeah. Triangle, quadrilateral. But the regular polygon here is an equilateral triangle and a square. And all these ones we call regular, pentagon, etc. So this is a pentagon, hexagon, heptagon. If you say septagon, I suppose it's okay, but I think heptagon's the official term. Octagon, nonagon, decagon. I don't believe... Not only have we not come across this, but I don't believe I know the name of this one. 12-sided shape's a dodecagon. Okay. And you might see in problems, I mean, not like on this exam per se, I don't know, maybe, but you might see problems where they say an n-gon, if something's n-gonal, or a 15-gon, or whatever it is. I mean, heck, you might even say 4-gon, whatever it is. This means the number of sides in the shape. If it's a 15-gon, there are 15 sides in the shape. 4-gon, 4 sides in the shape, which is a quadrilateral. You know that. But an n-gonal shape is something assuming you don't know the number of sides or whatever it is. But it determines the number of sides, not the number of degrees on the inside. Okay. So we have that information there. Now to work with central angles here. Let's go with green. We haven't done green yet. Regular polygons all have a center. In that you can extend certain parts of your polygon to this one midpoint. In this case, from your vertexes, from your angles, to the center here, you can create these, which are called radii. Okay. Now, you have heard of a radius before in circles, but if this is your first time having heard about radii in polygons, technically not your first listening to the video, But if you haven't been hearing about these prior to, let's make sure we get a good understanding of them. Okay, because radii, in circles, they're used to say that, well, I mean, I won't draw it, but, they're used to say, I go from the center to any point on the circle. But in a polygon, there are only in a regular hexagon, there are only 6 unique points that are this distance away, and they're the farthest distance away from the center as you can possibly get as far as points on the hexagon. So there are radii there, and let's go use an orange here. There are these other things. One of them, I still don't know the plural, but this is called an apothem. So we'll go and distinguish the two, and then we'll start talking about right triangles. Okay. The radius. One radius is the farthest distance away you can get from center to the farthest point away on your polygon. The apothem is the shortest distance away you can get from your center to your polygon. And we've talked about that before. The shortest possible distance between a point and a line, between a point and a line is the perpendicular one. Look at that and you say, okay, that's the shortest distance. Obviously, these get further out as you go. So whenever we find the apothem, not only do we create a right triangle with it, but we accumulate that shortest distance we can go, which is pretty cool. What do these help you do? Well, a couple things. This radius, for instance, it bisects your interior angles. So as we discovered, this is 120 degrees. When you draw a radius through it, it bisects these into 60-degree angles. Okay? Even if you didn't know that, what you could do is you could suspect, okay, if these are all radii, then they all must be congruent. If these are all congruent, then I'm looking at isosceles triangles. So if I draw this red right here, you can see this is an isosceles triangle. In fact, in a hexagon, it's an equilateral triangle, but let's not go there for now. This is isosceles because these two are congruent. If these two are congruent, that means these two are congruent. And if, etc. And so are these. And because all these are congruent, doing their own thing, these are all 120 degrees, so that means these must be congruent in retrospect. I'm looking at 60-degree angles here and here. And because of that, then my central angle, which we'll now talk about, which I wanted to get into, my central angles are now the difference of that. There are two ways of finding central angles. A central angle are the ones that are made by the radii, not by the apothem, but by the radii. Well, I suppose they're made by the apothems as well, but I don't want to say radius and apothem. So this is one central angle. There are 6 central angles in a hexagon. In an octagon, there are 8. In a decagon, there are 10. In a quadrilateral, there are 4, etc. They're all made from the center. They all go out, and they're formed from here. Now, as you can imagine, they are also congruent. Okay, and because they're congruent, you can add them up. They create a circle. They go full rotation, so they're 360 degrees. So the measure of each central angle is taking 360 degrees and dividing by the number of sides, or the number of central angles there are. Okay. Now this is just like exterior angles, so I don't know if it connects with you, but these are always the same measure. So the good news is, if you know one, you know the other. Or if you need to know one, use the other to help you out, etc. You divide by the number of sides, but you work with what's given. You really work with what's given. Okay, so central angles might help us then start determining things about these triangles within. And we need these triangles super importantly because this apothem height will be crucial to our understanding of the area of a regular polygon. Okay, I'm trying to decide if I want to get into that right now because I know that that's a whole nother thing, Pythagorean Theorem, etc. So let's see if there's anything else we need to know here. Okay, theorems and axioms are kind of a no here. Let's go ahead and start talking about other terms though. Okay, so all those are there. New terms. You started to learn about perimeter. not that you didn't know what perimeter was. I'm sure you've known that since, I don't know, since maybe in 4th grade. But you're starting to get 2 new looks on perimeter. One of them has to do with these polygons here. Because we learned the area of polygon, it has to do with using the perimeter. We started talking about finding the area of a polygon by taking the area of each triangle, for instance, and multiplying it by the number of triangles there are. But then we figured out when we started working with our formula, your perimeter is also equivalent to taking one of these bases of your triangles, like say this is the base of this triangle here, and you multiply it by the number of sides. So perimeter can be looked at in a different way. You can add up the sides, yeah, but it's also, you know, if every side's congruent, you can multiply it by the number of sides if you know one of these things. Or if you know half of it, you have to multiply this by 2 and then by the number of sides, etc. So there's kind of just a unique way of understanding that. The other way we've looked at perimeter just a little bit, we don't really call it a perimeter this way, is with circles. A circle has a circumference, and again, like I said, perimeter, we've always said, oh, you add up the sides. But a circle can be a part of a perimeter. It can't not be. So there's still a perimeter around here. We call it the circumference, but it's not defined by adding up all the sides, because there aren't any sides in a circle. So in this case, the perimeter is just the length of the outside area. So that's always how we're referring to perimeter and how we look at it when we do this. So perimeter in this case, oh, and one more thing is, again, when we talk about circles, and you know, I should probably start talking about them now because we're going to do more terms here. We can find portions of a circle or of a polygon. But for instance, this thing right here, this is called your arc. Your arc is just a portion of your perimeter. So if you know the perimeter, then you look at what portion this is of the circle, what part of, you know, what fraction of the circle am I covering, and that's the length of your arc. Okay, so we talked about portions. We use that with a central angle, and we figure out what the measure of the central angle is. We compare that to 360. So let's talk about the word proportion here. Again, I know I'm jumping all over, but this is more of a listening thing than anything else. It's review, so it's not things you haven't learned before. If I find out what proportion this central angle is out of all 360 of this, then I can find out what the measure of my arc is by comparing it to the perimeter, or the circumference. I should probably now write that word. The circumference of my circle. So for instance, if this was 90 degrees, 90 degrees is 1/4 of 360. You would set up 90 over 360. That's equal to some arc measure, which I don't know, over the entire circumference. Let's say it's 14 pi, whatever it is. You know, I think we used that one before. Let's say 12 pi. And this is 1/4. It's going to be reduced to 1/4. So now you cross multiply 4x equals 12 pi, x equals 3 pi, let's say inches, whatever it is. So while the entire circumference is 12 pi, this is just 1/4 of it, which is 3 pi. So that's kind of how arc works, and we talked about that using polygons as well. If we need to find out, instead of the whole perimeter, let's find out just a fraction of it, like those two right there. An easy way really is taking a length. Let's say this length is 6. You multiply it by 2. You get a length of 12. But you can still set up a proportion. Find out what this central angle is. And then just create a proportion that way. So it's not impossible to do. Okay. With regard to everything, we've talked about area. Okay. This is a big term. Used often. And I can use it in a lot of different ways here. And I guess I said that this would be a short thing. I mean, you know what? I think I'm going to check off boxes as I go because I'm using all the terms right now, and I think I'm covering a lot of these as I go. So the area of a polygon can be found in multiple ways. You know, we started with areas of triangles way back when, and areas of rectangles and stuff, and we did all the different quadrilaterals, and we figured out. Excuse me, let me get yawning. We figured out how we get the area of any of these quadrilaterals, and they all have a basis of triangles. They all have to do with triangles in some way or the other, and that's how the formula comes to be. Or we just, you know, we can use triangles to make sense of the area. Here's the same thing. If I have these triangles, okay, if I have these triangles, and keep in mind they're isosceles triangles here, they're all congruent. So if I find the area of one triangle here, I can multiply by the area of all of them, and then you get, boom, you get the area of your entire shape. The area of shapes, the way they work, because we've looked at strange quadrilaterals before, and really strange shapes. If I give you this shape here, and I say find the area of it, and I say these are right angles, I say this is 6, this is 4, and this is 8, okay? You're saying, well, I don't know how to do that. This doesn't make sense to me. I've never seen this shape before. I don't know the area of it. Well, I guess technically this is a trapezoid, but let's forget that for now. Let's say, well, you can divide this into two different shapes. Because these are right angles, what if I just created right angles out of here? And because these are supplementary, etc., this is now a right triangle, and this is now a rectangle. And if this is a rectangle, then this length must also be 4, and this must also be 8, and this must be 2, etc. And I can use Pythagorean Theorem to find this out, and then it's blah, 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 blah. So you can find it out. And now you say, okay, let's take the area of this, whatever it is. Actually, I guess you don't need that for area, but you need it for perimeter. You say, okay, I find the area of that, I find the area of that, and I add them together. That must be the area of the entire thing. And that's one way that you can construct areas. Find the area of the entire thing when it's enclosed. You can work through it that way. So if there are 6 triangles, find the area of one, add them by the rest. The important thing here, and I might as well get into angled side relationships while I'm doing all of this, because I've already exhausted everything else as I'm going here. And again, I understand I'm jumping around. This is for your benefit to kind of just listen as you go. Let me bring this down. Paste it down here. Because I've been working with this hexagon for so long. Let's say I want to find the area of this triangle right here. Okay. Looking for that area, and I'm going to use actual values, because I know when we did notes it got kind of funky looking. Let's use, I don't know, I guess we've used 10 a lot before. Let's go and use 10. I have a base of 10. A side length of 10. They'll say, find the area of a regular hexagon with a side length of 10. Not necessarily my test won't necessarily ask that specific question, but we do things using areas and such, and that this will be important to you still. Okay, this kind of concept, knowing what this means, why this works. So here's a radius. Here's an apothem. The apothem is so crucially important for this, because this is like the height of your triangle. So even if you're finding the area with 1/2 apothem times perimeter, which we found by using areas of triangles and adding them together, you still need to find it. So let's look at one right triangle here. This guy, that's the orange, the black, and the red. Making one right triangle. And here's the important stuff you need to figure out. If you only know it's a regular hexagon and a side length is 10, I can still extrapolate everything from that. Okay. A regular hexagon has interior angles of 120 degrees. Half of that is 60 degrees. Right here, when the radius bisects it. So this is 60, this is 90, this must be 30. Although mine's not drawn to scale, that's a 30, 60, 90. And this side length right here is known because it's half of 10. This apothem bisects... One second. This apothem bisects this side length into two congruent parts. So that's a 5. Even if you didn't know that, I do believe we talked about how an isosceles triangle, if you draw an altitude from it, it makes a perpendicular bisector. Okay, so we have a 30, 60, 90, and the shortest side, the side opposite 30, is 5 units, 5 whatever it is. And there's a special relationship in these triangles. So I'm going to talk about special triangles right now. That's this guy right here. Angle and side relationships with special triangles, 20. Let's go ahead and create real right triangles and make it look a little better. Well, pretend like these are different. You have a 30, 60, 90. and a 45, 45, 90. These have special relationships, and another bell's about to ring. Okay. So 30, 60, 90 triangle. If the shortest side is x, and I like to refer to the shortest side, that way I only need to multiply as I go up. I have a special, again, special relationship. This is x times the square root of 3. Now, if you didn't know that, you can use trigonometry and you can approximate it, but let me talk about the difference between an approximation and real an exact value for a second. X times the square root of 3 is exact. When I refer to this radical here, by radical I mean a root, some sort of root right here, this is an exact value. If I approximate it to whatever it is, it might be like 1 point, I can't remember, it's like 1.6 or 1.7 something. But see, that's the point. I'm only approximating when I say that. This is some exact 1.72408, it's some big number. That's important. Maybe for your answer, maybe not so important because, they say, okay, round to the nearest tenth at that point. Now you've truncated it. But I'm trying to find the area of this entire hexagon here. And if I round this number right here, and then I do some multiplication, apothem that's rounded times a perimeter, and then I go and round that value after, you can see why it starts to become an approximation of an approximation of an approximation, etc. Like when we did that big pentagon problem, I'm asking you to round everywhere. No big deal because those are big numbers. I'm saying, hey, I want to make sure you know what you're doing. Not exactly that we find the area of the floor plan of the pentagon, but you need to have this understanding that when you round, especially with such big numbers like that, you're going to be losing so much information. If I, for instance, the pi is 3.1415926, etc. It keeps going. 53, I think 5359 or something like that. It keeps going, but if we just approximate at 3.14, look at how much other information we're losing. And maybe with small values it's not so important because maybe sometimes we only round to the nearest tenth, etc., and we have small numbers to deal with. But when you use pi and you're using a circumference of something in the millions, a radius of something in the thousands or millions, now look at how much you're losing. What's the difference between the number, if you're making money, what's the difference between $3 million and $3,141,000, etc.? That's money. That's not chump change. I want that money. You know what I mean? So don't lose that information. Use this value pi when it's exact and appropriate. It doesn't help you get an understanding of what the number is, but I know that root 3 is more than 1. So, I think that's good enough for me to know that this is a greater value. Anyway, back to special triangles here. This is 2x. This is twice. The one opposite the right angle is twice the amount of the one opposite 30. And if you don't know this, again, two different ways you can figure it out. If you know these two, use Pythagorean Theorem. As long as you do it appropriately and you know how to get x root 3 squared, which is 3x squared, then this is possible for you to determine. And if not, then use trigonometry, and we're going to talk about that. You know what? Hang on a second. Okay, I'm resuming play here. Sorry, I actually did pause this video. I guess you wouldn't have known it. I'm kind of missing a standard here. A standard 19. It says students use use trigonometric functions to solve for an unknown length of a side of a right triangle given an angle and the length of the side. So I will glance over trigonometry because it's going to be important, just just in the long run, getting the understanding. But I glanced through my exam, and I don't believe that any physical, having to use the calculator for trig is going to be important. The concept of trig, however, will, saying I have to use trigonometry when I don't have special triangles. So okay, let's say that we have we did 36, 90. Let's do 45, 45, 90. This is x. Notice 45, 45, two congruent angles, and then one that's not congruent. This is an isosceles right triangle. If this is isosceles, these are both congruent. If these are both congruent, this is also x. So here you have relationship x and x for both these legs. Now the hypotenuse is x times the square root of 2. And again, if you don't know that, what you do is you take these, use Pythagorean Theorem, x squared plus x squared. You get 2x squared. The square root of 2x squared is x times the square root of 2. So Pythagorean Theorem, again, super important here. A squared plus b squared equals c squared. And make sure that you understand the radius is the c squared, or is the c, it's your hypotenuse, and the apothem is your a. Well, you know, it's a leg. So maybe you're given the radius, and it's like, okay, how do I find the length of a side? How do I find the apothem, etc.? You start using Pythagorean Theorem, your special triangles, etc. You have to make sure that you notice which one you have and which one you can determine based on it. Now, the whole concept of trigonometry is that not all polygons are derived with special triangles. You're lucky that a hexagon happens to give you special triangles. But then you look at something like even an octagon. I'm going to kind of avoid heptagons as much as possible, but you know, I go ahead and I look at this. In fact, I'll make it pretty big. I want to make sure you can really see everything in it. I do an octagon here, and I start from, you know, these whereabouts with the center, and I make a right triangle out of it right here, and you get, you know, you have a right triangle, which is great, and you even have pretty clean values for exterior and interior angles because they're not decimals. But now you start running into some issues here. Each central angle, which again, central angles are the full guys right here, is 360 divided by 8, which is 45. So the entire thing right here is 45. Problem is, this is only half of 45. Half of 45 isn't a very pretty number. It's 22 and a half. This is 22 and a half. This is whatever 180 minus that is 157 and a half. No, I'm sorry, 90 minus that. Must be 67 and a half. Okay, not very pretty numbers. Better yet, they're not special triangles. Okay, it's not a 30, 60, 90, 45, 45, 90. So if I have a side length, like, you know, 5, okay, I can't say this is 5 root 3. Okay, this isn't a regular, I'm sorry, you know, this isn't a special triangle. Okay, this isn't the triangle relationship here. So I have to work about it another way, and that's using trigonometry. So at this juncture, because we haven't been doing too much of it, it's not like I'd expect you to know it well, I can kind of. But I'd say use something that you do know with this. It is a right triangle, so I can say like the cosine of 67.5 degrees is 5 over x if I want to find that. Or if I want to find this, I'll call it y. We'll say the tangent of 67.5 degrees is y over 5, etc. These are ways you're going to figure it out. Trigonometry. Okay? There are only certain regular polygons that give you special triangles. Special right triangles, and that's something which is kind of important to determine. It's based on your central angles and your interior angles and how they divide. Okay, but you're going to want to look at all those and figure out which ones give you special triangles, which ones don't. Okay. For instance, an octagon doesn't, a hexagon does. Yeah, and special triangles 30, 60, 90, 45, 45, 90. Okay, so like I said, we kind of did a lot already, and I'm going to be able to cross off things as I go. Right now kind of check off what I know I've kind of talked about. We talked about Pythagorean Theorem so much, I'm not sure I can really explain too much more about it. You know what Pythagorean Theorem is, you just have to recognize when you should use it. And really, with all these apothems and such, it's going to be important. Okay, prove relationships of angles between polygons by using properties. So I want to talk about that a little bit more. We're pretty close to making sure we have all of it. That was saying interior and exterior angles are supplementary. So when I said angle relationships, prove relationships of angles, we're talking about supplementary angles, complementary angles, okay? Vertical angles, right? Where do you have vertical angles? Not just here, which you can recognize. These two radii, or these 4 sets of radii cross through. This is 45, so is this. Whole thing is 45. You got vertical angles. It also appears in circles. Let's go back to that circle I drew right here. If I draw two diameters, which diameter is another term I guess I should talk about. If I draw two diameters through the circle, I've created vertical angles here and vertical angles here, and they're congruent. Not only that, I've created adjacent supplementary angles here. Because you know diameters add up, or are 180 degrees for the circle. These must add up to 180, so are these, etc. So we're looking at a bunch of different relationships there. There are also complementary angles. One that we don't talk about too much here is in triangles, in right triangles, these two guys add up to 90. Okay. Now I'm sure you probably knew that, and I'm sure you can perceive and notice that, but see why it makes sense. All triangles add up to 180. This one is 90. Then these two together must be 90. Okay. Again, I'm going to say that again. Make sure it makes sense. If you have a right triangle, again, triangles add up to 180. One of your angles is 90. The other two must add up to 90 then. They must. It doesn't matter what they are. I mean, look at this one right here, 22.5, 67.5. These must add up to 90. Normally what you guys might do is say 90 plus 67.5 plus this equals 180, so do 180 minus whatever these two are added together. You don't have to. Just say these add up to 90. They are complementary angles. Okay. Making sure you fully understand angle bisectors here. The apothem bisects your central angle. The radius bisects your interior angle. Okay. Yeah, let's see what else to say about the interior, etc. Okay, so making sure that makes sense there. What are the relationships? Not too much there, but while I'm on the concept of interior angles, let me bounce back down and talk about that here. We said interior angles don't add up to 360, so what do they add up to? A question that we always kind of don't remember the answer to. Okay, I'm going to take triangles like this, and I'm going to duplicate them and rotate them and have fun with them. Here's a triangle, okay? Ignore that one, look at this one. Here's a triangle. If I add another triangle to it, and I close in this gap, let's see. Flip it around. If I add another triangle to it, I've created a quadrilateral, looking at the outside only. Okay, let's add another triangle to this. Boom. I've created a pentagon. 1, 2, 3, 4, 5-sided shape. I add another triangle to it. Let's see. I'm not really sure how I'm going to make this look pretty. As you can see, what I'm doing is I'm adding triangles, and I'm trying to create more shapes out of it. Now I have a 1, 2, 3, 4, 5, 6-sided shape, a hexagon. And again, if that's like, I can't see where that hexagon is. It kind of looks like that. Sorry, these are two different angles right there. So it's a hexagon. It's not a regular hexagon, but it's a hexagon. It's 6 sides. So you can notice when I add triangles onto my shapes here, I'm getting a different polygon than I had before. A hexagon, now all triangles add up to 180. We know that. So the angle measures, I don't know what these angles are necessarily, but I know that together these combine to create one of the angles of my polygon. Same with this, same with these three, etc. So all of these combined are the same as these angle measures combined. So 180 plus etc. or 180 times 4 is 720. So in a hexagon, even in this regular hexagon way up here, which were all 120 times 6, these are 720 degrees. Doesn't matter if your hexagon's regular or irregular. Now, if it's irregular, that means all these are not 120 degrees. Maybe there are other ways you can find them. You know, add up, this, and that, whatever you're given. One's a right angle. These guys are congruent, etc. Okay. So interior angles. How do we find out the measures besides looking at a table? Well, okay, we do have to start with the basis of a triangle, understanding, because we did prove that triangles add up to 180 degrees by talking about that on the first unit exam, Unit 6 exam. So they add it to 180, and we understand that a quadrilateral is two triangles by drawing the rectangle, and then by drawing the diagonal in between them. So this is two triangles, and it doesn't matter how you work it out. It's always, it's always two triangles, and two triangles add up to 360, etc., and adding the triangles and so on and so forth. But you notice here, I have 4 triangles and 6 sides. When I didn't have this triangle earlier, I didn't have it, I had 3 triangles and 5 sides. When I didn't have this one, I had 2 triangles and 4 sides. When I didn't have this one, I had 1 triangle and 3 sides. Okay, you notice this relationship here, that the number of sides in your polygon, and you might want to write this down somehow, the number of sides in your polygon is always 2 more than the number of triangles that make up the polygon. So for instance, 2 triangles make up a quadrilateral. 2 triangles means 4 sides together, because these shared sides that come, these shared sides that come about. When I had another triangle here, it's 3 triangles. Now it's 5 sides. It's always 2 more than the number of triangles you have, or the number of sides. Sorry, is that what I said? Yeah, the number of sides is always 2 more than the number of triangles you have. If I have a 10-sided shape, that's made from 8 triangles. So the way that you figure out this, so there's a relationship here, and we use this formula. It's derived from this understanding. If n is your number of sides, and d is the interior angle sum, okay, not the measure of each interior angle, not the measure of each, but the interior angle sum. So like 720 degrees, for instance. 720 degrees means 4 triangles. That's why when we divide both sides by 180, like if we use this right here, we say 720 equals 180 times n minus 2. We want to figure out the number of sides, even though we know it's 6. We divide both sides by 180. We do this mathematically because we're trying to solve for n, but we do this in theory because we're saying, okay, we have some amount of triangles. I want to figure out how many triangles there are. If all triangles add up to 180, and if I divide this by 180, then how many triangles do I have? And 720 divided by 180 is 4. So 4 is n minus 2. And we know that the number of sides in your shape is always 2 more than the number of triangles. That's why we add 2 to both sides. Again, despite the math. So n is 6. So it's a 6-sided shape, or a hexagon. Now, this did not tell me if it was a regular hexagon or not. If they did say it's a regular hexagon, then they're like, okay, it's a regular hexagon. What's the measure of each interior angle? Well, now you can take your 720 that you originally had and divide it by your number of sides. You get 120 degrees. Okay, so there's a way you can work through all of these, work around all of them. And now we're like, okay, what's the measure of each exterior angle? We can do 180 minus 120. Or you could have originally done, or once you found this out, you could have said, okay, it's a 6-sided shape. I can do 360 over 6. Because that's the number of exterior angles, and they're congruent. It's a regular hexagon, etc. So those should match up. So there's a way to connect all of those. Okay, definitely a way to connect all of those. I need to talk about area again. I just forgot. There's something that I completely blanked out on. 2 things. One is in circles, but the other is this understanding of when polygons. I was talking about this. When polygons aren't exactly the polygons we know. We've talked about things like in your homework, you have like a track. I'm gonna first pretend like I can draw a decent looking track, or maybe I have a semicircle. Nope. I'm gonna makeshift a track here. Pretend this is straight and curved and straight and curved. And it's like, okay, well, we have some information. Maybe we know this length. It's like 30, and I forget what all the lengths were. Maybe this is like 60. Whatever, try to find this out, and we're like, okay, what's the area? Okay, well, this is an irregular shape. It's not like an oval, whatever. It's that this divides into separate shapes. Here we're looking at a rectangle. Should really erase some of this stuff, but we're looking at a rectangle, and we're really looking at two circles. Okay, if you imagine again. Saw those values there? There was 30. Like this is 30, which looks like the radius of my circle. And this is 60, which looks like the length of my rectangle. What's the height of my rectangle? Well, it's twice 30. It's also 60. I guess I screwed that up. But this is also 60. Okay, so I can find out the area of this rectangle. Then I can find out the area of a circle, which we'll talk about in a second. And then I can find out the area of another circle. And I can add them up, and boom, I get my area. But wait, I don't quite get my area because I've created overlap. You can see where the green and red conflict. You can see where the blue and red conflict. I don't want to count those twice. So maybe what I do instead of that is I find the area of this rectangle. And then you can either do this one of two ways. I can find half the area of this circle and half the area of this circle. So find the area and divide by 2. Okay, those are sectors of my circle, something else I haven't yet talked about. I should have put that right next to arc. Sector is finding the area of that place created by a central angle, or created by whatever. You do the same thing. You set up a proportion, and you compare it to the area of the entire thing. So like I said, when I want to find this sector right here, I find the area of the entire circle, and then I divide it in half. Area of the entire circle and divide it by half, in half. Okay, so I either do it that way, and then I add all these three things together, or I find the area of this rectangle, and then I know both these circles are congruent, so I say, okay, well here's half and half, they make a whole. So I just find the area of one circle. So if I find the area of this rectangle, the area of one circle, and add them together, I get the area of the entire thing. Okay. We've also talked about areas of shaded regions with, like you get a square and you get a circle inside it. Okay. Like I want to find the area of, say you want to find the area of this, of the shaded region here. We talked about this. Okay. Well, the important thing is, let's find the area of the square. Let's find the area of the circle. And then let's find out the area of all these guys here. And that's taking the area of this, your square, and subtracting the area of your circle. It's like cutting it out. Because before, this is the area of everything, your square. If I take this area out, the area of my circle, I'm just left with these. And assume all these to be congruent, so you can divide by 4. And then boom, just get the area of one of them. Alright, so there's like a way to do it. And remember, when we find the area of a circle, we're definitely working with pi a whole lot. So make sure you leave exact answers in terms of pi as long as you can. At least until your very last answer. Because you don't want to round, you don't want to do approximations of approximations. Okay. Let's see what else I need here. We talked about these. Okay, I know I haven't gone over this yet, so I'm just about done. The other teacher's going to come in soon, and she's probably going to cut me off, and I'm going to have to resume it later, maybe. Let's talk about circles a little bit more. We've talked about those. So, by the way, area of a regular polygon, most commonly known as 1/2 apothem times perimeter, or 1/2 base times height of a triangle. Keep in mind, that's just of a triangle, like this base, this height. And then times n, which is number of sides. I'm just making sure I'm clearing off that one. Okay, let's finish off circles here. Going way down. Going way, 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 way down. In the deep abyss. Circles are awesome. Circles have one defined center in that every distance away from the center is equidistant. And these distances away from the center are called the radii. So everywhere you can draw an infinite number of radii in a circle, whereas in polygons it's only bound by the number of angles in your polygon. But here in a circle, like I said, you draw a radii, you have some sort of length here, okay? The diameter cuts through the circle, or I'm sorry, it goes right through the center, so it's like 2 radii put together. This is the longest segment you can make in a circle. We use this with, we talk about pizza, etc. Like, we got a 10-inch pizza. Okay, 10-inch pizza. We're referring to the diameter. If you need to find the circumference of this, we refer to pi, and pi is a constant term. We talked about it, 3.14. It's the relationship between the circumference of your circle, this guy here, and your diameter of any circle. I don't care what the circle looks like. Well, and obviously they're all circles, but I don't care how big or small it is. You take the circumference of a circle, use measuring tape, and you measure exactly what it is. Okay, so if you're watching, this is going to end up being a bit disjointed. I was cut off earlier this morning because more teachers and such came in and whatever, so I couldn't keep recording. So now I'm back and we're on the same screen like 4 hours later. So I believe I was talking about pi. I mean, it's pretty obvious it's on the screen. Anyway, pi is a ratio. It is a value. I'm sorry, let me start with that. Pi is an actual number, 3.14, and I know we talked about that. Okay, this is actually chugging. Et cetera, et cetera. So that's an approximate value. But it's a ratio of any circle's circumference to diameter, to its diameter. And that's any circle. It doesn't matter how big or small the circle is. That is a ratio. You take the diameter, use a measuring tape. I think this is what I was talking about before I got cut off. Take a measuring tape, get that circumference, divide it by the diameter, and you get 3.14, 1596, etc. So in that regard, you can also find the circumference of a circle by taking the diameter and multiplying it by pi. So the circumference equals diameter times pi. Okay. I'm uploading the first portion of the video right here. That's why this is getting really choppy. So if there are ever issues, I guess that's what we're going to have to do with it. And the circumference also, see, the diameter is twice the radius. If this is the radius here, this is also the radius. Okay? So it's also 2 times pi times the radius. So there are two different ways you can look at it. Diameter and 2 times the radius are both interchangeable. Okay. Remember, the circle is the outside. It's this rim, this black thing. So you can find the length, the circumference of it, or the perimeter, so to speak. The area is the inside, though, this filler. What is inside the circle? How much coverage do I get? And without going into detail, because we did in the lecture notes for it, the area of a circle can be found by squaring r and multiplying it by pi. Area is pi r squared. I think you hear that a lot. Doesn't matter how old or young you are. Everyone kind of has heard that before. Pi r squared, pi r squared. So, yeah, if you take a radius and you square it, you can make a square out of it. You multiply it by pi, you get that same ratio. And again, there's a way we figured out how to do it, but we'll save you for that. So, excuse me. So you have these two different methods of finding these two different things. Okay? But now what we're going to do is take portions of our circle. What if I wanted to find the area of just this, what we call a sector right here? And we talked about sector earlier. Okay? Remember what I said before up top. Find the area of a sector, this green thing. Find out what portion of my circle do I have covered. And it's based on your central angle. If I find out what the central angle is down here, okay, if I find out what this is, like say it's 70 degrees, okay, you set up a proportion. You say, well, that's 70 degrees out of a whole 360. And that's going to be equivalent to what my area I'm going to find out is over the area of my circle. Now, in most cases, you're going to know what r is. Maybe it's 5, in which case your area is 25 pi. So whatever this is, it reduces to 7 over 36. You're going to take 7/36 of your area here. Okay. Same thing with perimeter. Whoa, I'm glitching. Whoa, glitching up here. Okay. All right, so the same thing with circumference. If I wanted to find how long this green portion is here, set up a proportion. What's 70 over entire 360? Okay. And that's the equivalent to your x, the thing we need to know, out of what the entire circumference is. So that's what setting up proportions is all about. And that's how circles work. Like I said, I wanted to try and keep this short. So I'm hoping that's short enough. I'm hoping that works with what we need to do for circles and such and their properties. And if we need to know more, I suppose there are different ways we can use it. I used most of it in that video, though, so I don't want to keep going with that. And the final one, understand how changes in dimensions affect the perimeter and area. So I can go all the way down here. There are these things. We're going to call them RS, RP and RA. This is ratio of sides, perimeters, and area. Okay, this is glitching. Ratio of sides. Ratio of sides, perimeters, and areas. So basically, if you have two similar figures, it doesn't matter what they are, but let's go ahead and use rectangles. I have two similar figures. Assume they are the same. Similar means congruent angles and same side ratio. So ratio of sides. Let's say this length is 1, this is 2. This is 3, this is 6. Okay? And assume the rectangles, all right angles, etc. Okay, my side ratio is 1 to 3. You can even test this here. 2 to 6 is also 1 to 3. So ratio of sides, 1 to 3. Ratio of perimeters here. This should also be 3 and 6, 1 and 2. My perimeter, 1 plus 2 plus 1 plus 2, is 6. So that's 6 to 3 plus 6, 9. 3 plus 6, 9, 18. 6 to 18 reduces to 1 to 3. So ratio of sides and perimeters, this is just one example, but it's true all the time. Your ratio of sides and your ratio of perimeters are the exact same. Ratio of areas is not. This is base times height, 1 times 2, that's 2. 3 times 6 is 18. 2 to 18 is not equivalent to 1 to 3, it's 1 to 9. Okay? So ratio of area, what you do is you take the ratio of sides and you square it. You'll get the ratio of area. Take the ratio of perimeter, you square it, you get the ratio of area, because they're both the same thing. 1 squared is 1, 3 squared is 9. So if you want to go from ratio of perimeter to ratio of area, that's what's going to happen. And the way that this works, really, I'm going to have to shrink this a little bit for it to even look accurate. Let's see if I can. Okay, so let's pretend that this actually is perfectly 1 to 3. So this is 1, 2, 3. Right, so I'm looking at the length here. This side length is 1. It takes 3 1s to get there. Same with here. 1, 2, 3. It takes 3 side lengths of 2 to get 6. Area is different. Here's one area of that small rectangle. 1, 2, 3. I have to move it over. 4, 5, 6, 7, 8, 9. So it takes 9 of these rectangles to cover 1 of the other rectangles. That's why we get a 1 to 9 ratio, and that's where it differs. So ratio of sides and perimeters are both the same. Ratio of areas is the square version of it. So if you have a side length of r, your ratio of areas is r squared. Okay? If you have a side length of r, your ratio of areas is r squared. So that's the way that the ratios work. Anyway, that's all I want to say about that. That's also in another section. Shoot. I can't remember. 822 or something like that. I think we did ratio of areas there. Anyway, I hope these work and they make sense and they help you out. If you have any questions, let me know.